Welcome everyone to this explainer. I am absolutely thrilled you're here today. Look, we are in the middle of a massive architectural shift that is completely redefining how we build software and systems. For the last decade or so, as developers, we've basically defaulted to the cloud, right? You collect data, you send it off to some massive centralized data center, you process it, and then you just sit back and wait for the answer. But what actually happens when relying solely on the cloud becomes your biggest bottleneck? Today, we're focusing on a guide for developers, really digging into the paradigm of local data processing. We're going to unpack this major shift from the traditional cloud to the device edge, explore exactly why it's happening, and figure out how you can architect your next big project to actually take advantage of it. Let's jump in.
To really wrap our heads around why this shift is happening, I want you to ask yourself a super simple question. Can your application afford to wait 200 milliseconds? Now, if you're building a standard web app, or a social media feed, then yeah, sure. A 200 millisecond delay to fetch a new image from a remote server is virtually invisible to the end user. But what if you're programming a self-driving car that's literally zooming down a highway at 70 miles per hour? Or what if you're coding the real-time control systems for a robotic arm performing remote surgery? In those critical scenarios, you simply cannot afford a 200 millisecond round trip for a server in some other city to tell your system to hit the brakes or to stop cutting. Some decisions just have to happen right here and right now.
And here is exactly why we can't just optimize our way out of this problem with slightly better cloud code. 7 milliseconds. This is a fundamental constraint of the universe. Even if your data is traveling over fiber optics at the literal speed of light, distance creates an unavoidable delay. If your user is interacting with a device, and your server is, say, 1,000 kilometers away, physics dictates that the data is going to take a minimum of about 7 milliseconds just to make the round trip. And keep in mind, that's before your code even starts executing. So when absolute real-time reaction is required, the traditional cloud architecture just fundamentally breaks down.
Section 1. The data deluge. Why the cloud isn't enough. 4 terabytes. That is the massive, almost unbelievable amount of sensor data, coming from cameras, LiDAR, radar, generated by just a single autonomous vehicle every single day. As the developer, really think about the bandwidth economics of that for a second. Trying to upload 4 terabytes of raw data to the cloud in real time over a standard cellular network, that's not just incredibly expensive, it is physically impossible with our current network capacities. If the cloud is the only place your code runs, an autonomous car simply cannot function, period. All of those driving decisions must happen entirely on board.
Section 2. Defining local data processing, moving to the source.
So what's the real crucial point here? Edge computing is essentially the practice of processing data at or near the actual source of generation. This means you're running your application logic, your machine learning models, and your data processing right there on the device itself, or maybe on a local server sitting right next to it, rather than defaulting to a distant cloud environment. For us developers, this means we are literally pushing our code to the very edges of the network.
Now, we have to realize the edge isn't just one specific place, it's more like a spectrum. Let's walk down this ladder together. Way up at the top, you have the traditional cloud, massive, highly centralized, but very distant. Moving a bit closer to the user, we hit the regional edge, which might be data centers distributed across different states. Step even closer, and you've got the local edge, like maybe a server rack sitting in the basement of an office building or an automated factory floor. Finally, at the very bottom, physically in the user's hands, is the device edge, the smartphone, the smart camera, the drone itself. As an architect, your main job is deciding exactly which tier your application actually needs to live in.
Section 3. Architectural trade-offs. Device edge versus cloud.
So how do we actually make these architectural decisions? Well, it really comes down to weighing the stark contrast between these two extremes. Let's break this down. If you decide to run your code on the device edge, you are getting hyperlocal, true millisecond latency. Plus, your bandwidth costs plummet because you aren't constantly sending massive files over the internet, and privacy is incredibly high since the raw data literally never leaves the device. But, you are heavily constrained by local hardware limitations and battery life. On the flip side, the cloud gives you near infinite scalability and processing power, absolutely, but that comes at the cost of second-tier latency, massive network bandwidth bills, and having all your users' sensitive data centralized in one remote location.
Let's ground this theory with a really practical example. Smart security cameras. If a camera relies totally on the cloud, it has to stream 24/7 high-definition video over your Wi-Fi to a distant server just to run an AI model that looks for intruders. I mean, that is wildly inefficient. But if you deploy an edge AI model directly onto the camera's internal chip, the device edge, the camera analyzes that video feed locally. It only pings the cloud, sending maybe just a few kilobytes of data. If it actually detects a person, it's a total game changer. It is dramatically faster, vastly cheaper on bandwidth, and significantly more private for the end user. Section 4. The Developer's Edge Toolkit.
The cool thing is, we are rapidly moving past the theoretical into actual, usable building blocks. First up, we have MEC, or Multi-Access Edge Computing. These are telecom standards that essentially put cloud-like compute resources directly inside cell phone base stations, literally bringing processing power to within milliseconds of a mobile device. Next, we've got hardware like NVIDIA's Jetson modules. These are essentially incredibly powerful GPUs packed into tiny credit card-sized boards that you can stick directly into drones, robots, and industrial cameras. Then, of course, there's 5G, a network architecture actually designed from the ground up to support this ultra-low latency communication. And hey, let's not forget CDNs, content delivery networks like Cloudflare, which have kind of acted as a proto-edge for years now by caching web content in distributed locations really close to users.
Section 5. Federated Learning. Privacy-preserving ML.
Now you might be wondering, if all your data stays trapped on individual edge devices, how does your AI ever get smarter? Well, the answer is the absolute elegance of federated learning. Here's how it works. Step 1, your application trains its model right on the local edge device, using the user-specific local data. Step 2, instead of sending that highly sensitive private raw data back to your cloud server, the device only sends the mathematical updates it just learned. Step 3, your central server aggregates all these tiny updates from millions of different edge devices, creating a globally smarter model, which it then pushes back down to everyone. It's brilliant. You get the vast intelligence of the cloud while maintaining the absolute privacy of the device edge. That's a massive win for modern architecture.
Section 6. Real-World Edge Architecture.
All right, we've talked about the physics, the theory, and the toolkit. Now let's look at some massive real-world industrial implementations of this stuff. Two of the most famous examples of cutting-edge tech out there today are entirely dependent on local data processing. Tesla's full self-driving? It does not rely on a constant connection to Elon Musk's servers. They literally had to design custom onboard FSD computer chips to process video feeds and make driving decisions right there in the dashboard in real time. Similarly, look at Amazon Go stores. When you walk in, grab a sandwich, and walk out, massive arrays of cameras and sensors are tracking your movement. To do that instantly without any lag, Amazon processes those extremely heavy video feeds on local edge servers right inside the physical store itself, not in some distant AWS data center.
But keep in mind, the edge isn't just about speed. Sometimes it is literally about survival when connectivity is just impossible. Take industrial IoT on offshore oil rigs, for example. These massive facilities have thousands of sensors monitoring pipes and valves for catastrophic faults. They need true millisecond response times to shut down a failing valve. They absolutely cannot rely on a spotty, high-latency satellite internet connection to a cloud server to tell them when to initiate a critical safety protocol. By using edge computing, the logic runs entirely locally, ensuring the rig operates safely, regardless of whether it's connected to the internet or completely offline.
And that brings us to a question I really want to leave you with as you architect your next platform. Is the future of your computing just going to sit safely in a centralized cloud, or does it need to live everywhere? Look, the cloud isn't going away. It's absolutely vital for heavy lifting, long-term storage, and global orchestration. But as we demand more real-time, privacy-first, and bandwidth-efficient applications, the cloud simply isn't enough anymore on its own. You have the toolkit now. The computation needs to move to where the data lives. So I challenge you to look at your current projects today and honestly ask yourself, what happens if I move this logic out to the edge? Thank you so much for joining me in this explainer. Keep building, keep exploring, and I'll catch you next time.